So first of all, we have a test coming up a week from tomorrow. So that's Wednesday, February 5th. The topics, I'll let you know by the end of class tomorrow, but probably what it's going to be is all the stuff that we've done so far, plus what we're going to start today. We should finish it by tomorrow, definitely by Thursday. So it'll probably be everything up through vectors. And all the exams, this one and all the other ones, are going to be just problems, sort of similar in type to the homework problems, okay, to the practice problems. So to get ready for the quizzes, you read the notes, skim the notes, try to remember, try to notice, make a mental note of what the big ideas are, that kind of thing. For this, you just want to work on the problems is the way to get ready for it. Okay, and the class hopefully is, my intention is for the class to just help you get ready to do the problems, and then the exams are kind of on how well you understand the thought process of the problems. Yep. No, there won't be. This will be all problems. Yep. Um, so to prepare for this, it's really just all about understanding the problems. The way I explain how like when you're ready, basically if you could go through all of the problems with like any problem someone picked out and explain to them how to do it, and answer questions about how to do it. So like you understand why you make this choice here, this choice here. If you can do that, then you'll do great on the test. It won't be the exact same problems as on the homework, but the thought process is intended to be the same. Okay, like with the methods you use on the homework, you can do and so I don't think you'll look at the test and be like, oh my gosh, I don't know how to approach this or whatever. It'll be the same approach you've used, just sort of slightly different setups, that kind of thing. Okay. Any other questions about the test? We can talk more about it as it gets closer. I'm not going to, no. So the practice problems are kind of the practice test. And then I just think of, it's like, I want you to get to the point where you understand all of those problems. And then it's basically statistical sampling is how I think of it. I just take a handful of those skills, kind of at random. Any other questions? Okay. Well, yesterday I went through a lot of homework questions. So today I'm just going to get right into new material. So the new topic is, well, what we're getting into is two-dimensional particle kinematics. Particle means that we're not dealing with the orientation of objects. Kinematics means we're not dealing with the causes, we're just dealing with position, velocity, and acceleration. 2D, so we were doing it along a line up until now, but 2D means that these things can now move in a plane. So they have more ability to move. But before we can get to this, before we can apply it to actual 2D particle kinematics, we need vectors. And so Before I get into actually applying this to kinematics, I have to describe the math of vectors. Okay, so remember that for one-dimensional particle kinematics, directional quantities, so quantities that have direction associated with them, quantities, and the directional quantities that we were dealing with were position, displacement somewhat, although we didn't use that very often, velocity, and acceleration. Sorry, leave off these vector things for now. So position, displacement, velocity, and acceleration. These were given by signed numbers. The plus or the minus indicated the direction. Remember, though, I mentioned this a couple times. It wasn't a big focus, but so these directional quantities could have always been given as a magnitude and an arrow. Okay, so for example, if we have a problem where something starts at a height of, 0.5 meters, and it's launched up into the air and then comes back down, we choose a 0 position and a positive direction. Okay, and based on those choices, and this thing is in free fall, what's the acceleration of this object? That's right. So the acceleration would be negative g, that's perfect, or negative 9.81 meters per second squared. Okay. But that's always equivalent to, so that's the same thing as saying down with a magnitude of 9.81 meters per second squared, right? That sign could have been indicated as an arrow direction. Okay, it's just that the arrow direction for motion along a line only has 2 possibilities. So this arrow only has 2 possible directions. Well, that's the idea of a vector, except that now if we go to 2 dimensions, and the same idea works in 3 dimensions too. Now in 2D, an object's possible direction let's see, that's not good. An object's possible direction has more than two choices. Okay, so in 1D, or motion along a line, if you have an object here, it can only go this way or that way, right? In 2D, you have an object here. It can go this way or that way, or any of the other infinitely many directions in the plane, right? So in 1D, there are two choices. In 2D, there are infinitely many choices. So representing the direction by a positive or a negative isn't going to work anymore. So direction can't be represented by plus or minus. It can still be represented by an arrow, though, and that's what we're going to do. Okay, so that brings us up to the definition of a vector. And a vector is a mathematical quantity with two properties. Or instead of quantity, let's say a mathematical object. So what's a mathematical object? Like, so a table is not a mathematical object, but a triangle or something is, okay? It's not something that's there in the real world, but it's a mathematical thing. You can imagine it. And this one has two properties. And these you need to remember. The first one is a magnitude. And the second one is a direction. You can think of that as an arrow whose magnitude is given by the arrow length. Okay, so for example, you can think of that as a vector, and if you measure it, the length of that vector tells you the magnitude of that mathematical object, and the direction is, the direction that it's pointing. By the way, two directions that'll come up every once in a while. So if we're dealing with stuff in 2 dimensions, then you can draw everything in the plane, right? But in 3 dimensions, you can't draw every vector. So a lot of times it's useful to have a representation for vectors that are coming out of the page or going into the page. So here's what people use. A circle with a dot in the middle is a vector coming out of the page. It's like you're looking at the tip of an arrow is the idea. And a vector going into the page is a circle with an X through it, like you're looking at the feathers of the arrow. One thing to keep in mind, so I said these are important. These are going to show up on a quiz at some point. But something else that's important to remember is that neither of those two properties is a location, okay? So a vector does not have a location. And so when we do calculations with vectors, we're going to imagine moving them around from this point to this point, because you can move them around and it doesn't change the value. The only thing that a vector contains is a direction and a magnitude. Okay. And before we talk about how we're going to do calculations, we have to talk about some sort of graphical, physical meanings of vector calculations. So I'll call this the physical meaning. And we're going to do two calculations. We're going to add two vectors. And we're going to multiply a vector by a number. And a number, another way to thing you hear numbers called is a scalar. So a scalar is, I mean, it's just a fancy word for a number, not that fancy even. But so we're not multiplying two vectors together. We're multiplying a single vector by a number. Okay, so the first one is adding vectors. So the idea is you use the two vectors, let's say 2, or it works for more vectors, 2. To create a path from a start point to a finish point, or to an end point. Then once you've done that, then the sum of the vectors which is called the resultant, is just the shortcut from the start point to the end point. Okay, so here's an example of this. So let's say that we have this vector and we want to add it to this vector. Okay, how are we going to do that? Okay, so I'm going to choose some starting point. It doesn't matter where because vectors don't have location. And I'm going to start at that starting point, take one of those vectors as the first leg of this trip. Then where that one ends, I'm going to put the second one. Okay. So this is the start point. This is the end point. And so the resultant vector is just the shortcut from the start to the end. Okay. What if I did them in the other order? Because you know when you add numbers, what? You come back here. When you add numbers, the order of operations doesn't matter. 3 plus 2 is 2 plus 3. So let's say that instead this is the start point. Okay. And then that takes us a little bit lower, and then from there we take this leg of the journey. So here's the end. And if you do it carefully, because location doesn't matter, this vector and this vector are the same. Okay. So the order of operations doesn't matter. And so now we're going to represent position, velocity, displacement, and acceleration as vectors. And what that means is if you have a case where you're adding two accelerations, okay, like we saw an example of that would have been in the relative motion equations that we did in the last couple of classes. If you have to add two accelerations, and one is this way, and one is this way, you add them using the vector rules, and the sum of those two vectors follows this physical meaning, okay? And if you did it carefully with angles and rulers and stuff, you could do this all just in terms of angles and stuff, okay? That's not how we're going to do calculations, but that's what it means. Any questions about adding vectors? Okay, what are the units of vectors? What? So yeah, it kind of doesn't have an answer. So any more than what are the units of a triangle or the units of a number? Okay, those are mathematical objects. The units come from whatever you're using this mathematical object to represent. So in the example that I just gave, where say these are accelerations, then these vectors would have units of meters per second squared. If you're doing it to add two positions, then they'd have units of meters and so on. Okay, so the vectors themselves don't have units any more than like a number has units on its own. Okay, so now what about multiplying a vector by a scalar? Well, multiplying a vector by any number, you can do it in two steps. So we're going to think of first what it means to multiply a vector by a positive number. And then after that, we're going to think about what it means to multiply a vector by -1. And with those two steps, you can multiply by any positive number, any negative number. Okay, so first, to multiply a vector by a positive number, keep the direction the same. And multiply the magnitude by the number, or the length of the vector by that number. So, for example, if we wanted to multiply 3 times this vector, no, we could do it like this. Don't worry, it's worth it. Damn it. Ah! Okay, so there's 1, 2, 3. And so the resultant vector is just this. Okay, keeps the same direction. The length changes by 3. Can you make vectors shorter by multiplying by a number? Yeah, the number just has to be less than 1. Okay, so what if you're multiplying by a negative number? Well, just think of going in order. First multiply by the positive number and then multiply by the -1. So to multiply a vector by -1, negative, Keep the length the same, and switch the head and the tail. So -1 times this vector is that. Okay, so to multiply a vector by -17.5, you make the vector 17.5 times as long, and then just move the head to the other side.
Can you demonstrate that with -17.5?
Yeah, with the copy. That'd take the next 2 classes. Okay, so this is a way that you could do all, with fine graph paper, and a straight edge, a ruler. You could do all your vector calculations this way. But we're not going to. We have an easier way. Using vector components. So vector components. The idea is that any two-dimensional vector can be represented as the sum of one vector parallel to the x-axis and one vector parallel to the y-axis. So, for example, if your coordinate system is like this, and you have this vector, okay, you can represent that as a vector like this, parallel to x, plus a vector like this, parallel to y. So this is the x component and the y component. These are always perpendicular. And those components, even though they're vectors, you can represent them with just 2 numbers. You can see that this x component is pointed in the negative x direction, And if you measure that length, you can just say the x component is negative 2 or whatever it is. Okay. And this y component is in the positive y direction. You can just represent that component as positive 1. Okay. So you can represent those components as an ordered pair of numbers. Okay. Just like you do coordinates. And this probably makes you think of coordinates of points, and you can think of it as equivalent to that. So this is equivalent to coordinates of points. If you put the tail of the vector at the origin of the coordinate system. So at the coordinate system origin. All right, so I'm going to take that same coordinate system. And that same vector, and I'm going to put its tail at the origin. Okay. Then the vector components are just the coordinates of the head of the vector. People write vector components a few different ways. So component notation for a vector. So let's say that the x component for an x component of x and a y component of y. The way I'm going to do it most often, I mean, I'll try to go back and forth a little, but is I'm going to use a column matrix with the x component on top and the y component on the bottom. There's some mathematical benefits for using that later on, because you can use matrix notation with vector components in a lot of cases. But you'll also see people write it like coordinates, and you'll see people write it like coordinates in whatever kind of brackets those are. And you'll see people write it as the x component times an I with a hat over it. It sort of looks like an Illuminati symbol. That's supposed to represent the direction of the positive x-axis plus y times something in the direction of the y-axis, so j. So all four of those things mean the same thing. And in different classes, you're just going to have to go back and forth between these a little bit. Physics people are more likely to use the IJ notation. Engineering people are more likely to use the bracket notations, but depending on what kind of operations you do, you'll see these in different classes. They all mean the same thing. So how do you calculate the components? Well, if you know one of these angles, You can use trigonometry, use SOHCAHTOA. You know that if you put the vector's tail at the origin, if it points in this direction, both components are going to be positive, positive, negative, 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 positive, negative. Okay, right? Just the same way as the coordinates. And so, yeah, you can always use SOHCAHTOA to do it. I think people who do these calculations in their head, you know, when you get used to doing them in your head, you do it sort of using SOHCAHTOA. But one way that always works, and since you always have a calculator in your pocket, you know, with phones especially, it's nice to always have a way that works. And also, I think this is nice for when you start programming stuff. So I'm going to give you one way that always works. For finding vector components. So let's say that the vector I'm going to use has a length of 10 and makes an angle of 20 degrees with the vertical. Well, first, we're going to put the tail at the origin. And if you use this coordinate system, it looks like this. Then second, find the counterclockwise angle from the positive x-axis to the vector. So in this case, we know that this is 20 degrees. And so it's 90, 180, 270, plus 20 is 290. Or you can go clockwise and call it negative 70. If you go clockwise, you just have to call it negative. Okay. And this counterclockwise angle, let's call this theta. And then the vector components are just the length of the vector times the cosine of the angle, length of the vector times the sine of the angle. So this angle is for this example is positive 290 or negative 70, and plus or minus any 360s. And so in our case, the length is 10. And we're multiplying 10 times cosine of 290 and 10 times sine of 290. The nice thing about this is you never have to think about the signs. The signs work out for you. And you get 3.42 negative 9.40. And do those signs make sense? The head is in the fourth quadrant, so you expect to have a positive x value and a negative y value, and that's what we got. And the magnitudes make sense. You know, you expect it to be a much bigger value in the negative y direction than it is in the positive x direction. And we got that too. Okay, so in math classes, I don't know if any of you have had math classes where you've talked about vectors yet, but for the most part in math classes, there's not really any reason to think about, to picture coordinate systems with different orientations. It's basically just a matter of like turning your head if you're only thinking about it mathematically. But in physics classes, the coordinate system is going to represent an orientation of math world compared to the physical world. And so there'll be times when we want to use funky coordinate systems. So let's use that vector that we just had. So let's say this has a length of 10 and makes an angle of 20 degrees with the horizontal. And we want to know what are the components in a coordinate system that's oriented like this, where this is the x-axis and this is the y-axis. We're going to do it the same way I just did it. So here's our coordinate system. This is x. This is positive y. And then I'm going to put the tail of the vector at the origin. I don't rotate the vector. You know, the part of the vector's identity is that it's in that direction, and it doesn't care what direction the coordinate system is. That's what the vector is. So I'm going to draw the vector here with the tail at the origin. And we know from the picture that this is 20 degrees. And now we have to figure out the counterclockwise angle from the x-axis to that vector. In this case, what's theta equal to? 110, yep. And so the vector components are 10 times the cosine of 110, 10 times the sine of 110. And so that is equal to negative 3.42, positive 9.40. That's what you get if you plug those numbers into your calculator. So there's going to be a lot of times in this class where we have a vector and we have to represent it in some unusual coordinate system. But the approach is always the same. Any questions about that? All right, well, it won't take very long, but next time, tomorrow, I'll talk about, once you have the components, what does it mean to add vectors? What does it mean to multiply a vector times a scalar? So we'll give an easy mathematical way to do these calculations that are equivalent to that physical way that I described earlier.